And I say we skip the things we're already familiar with. Is that cool with you guys? Yeah. Okay, cool.
Sounds good.
Starting off with coarser and finer topologies. Adar, you want to take this one?
Sure. So,
Do you want a whiteboard, by the way, to draw on?
yeah, let's bring up a whiteboard, although I don't think it's needed for like coarser and finer topologies. But yeah, if you have like two topologies, which actually let me be a slightly more rigorous. Let's say you have a set X and you have two topologies T and T. Then if T is a subset of T or T prime, then T is said to be coarser than T prime. And the opposite is true. Or sorry, if T is a superset of T prime, then T is said to be finer than T prime. And then if like T isn't a subset of T prime and T prime isn't a subset of T, the two topologies are said to be not comparable.
Really?
Yeah.
Interesting. Okay, I can see why. It makes sense.
Yeah, because you literally can't compare them.
Yeah, exactly. Yeah.
And this kind of like terminology makes sense if you think about it, because if this is true, if T is a subset of T prime, then that means T prime kind of contains all of the information that T contains, but also contains additional information. And so, yeah, that's kind of why it's called finer. Actually, I believe there's a better explanation if we draw stuff. So let's say you have like your set, right? It's something like this. Then like this could be like T. This could be T.
Oh, sure.
Right? And then if you wanted to have like something like T prime, then you draw, more subsets. And then just adding this one that I just drew, you also have to add this. And you have to add this. And then you could get even finer and you start adding, subsets around like individual points.
Yeah.
This would also make it finer. So yeah, just kind of like it contains all of the open sets that T contains, but also contains additional ones.
How about this trick sneak question? Sure. What is the finest and coarsest topology?
So finest would have to be the discrete topology, and the coarsest would have to be the indiscrete, or did you call it chaotic topology?
Yeah.
So just like just like X and empty set.
Yeah.
Yeah.
That's the weakest. Yeah. All right. Next one is, let's do subset. Or no, we already did subset topology.
We already did that, yeah.
That's one of the techniques of making new topologies from old ones. The second technique being quotient topologies. Yeah, quotient. The quotient topology on the quotient set. I think before product was quotient, but
okay, I guess quotient wasn't included in the list, but we can talk about that actually. That would be cool.
Sure.
There's just one thing I want to cover. I want to make sure we cover.
Yes.
And that's the difference between the product topology and the box topology, and kind of like why we have both definitions.
I'm not familiar with the box topology. Are you familiar? Are you familiar with it, Temen? If Temen's familiar with it, then I'm cool to learn it on the spot.
Here's the thing: the box, like if you understand the product topology, then you'll like instantly understand the box topology because they're very similar. But there's like a key distinction. But yeah, we can talk about that later.
Sure. Temen, you want to explain the
quotient?
Quotient, yes, that's what it's called.
Quotient. I'm trying to remember. It's been a few days.
Oh yeah.
So you have your set, you define an equivalence relation on it, and you declare each equivalence class to be its own open set, if I recall correctly. Is that how that one works?
Almost. Then you have an extra restriction, I think.
Then I have forgotten. Could someone please clarify for me?
Yeah, here, actually, I'll do something neat. Let's do this. You guys can actually write on this document. So if ever you want to like draw some stuff here, in this case, we've actually got the definition right here. So yeah, it's every element that's a part of the quotient set with the restriction that the preimage under Q of that set is a part of the original topology. Simple enough.
Yeah, why don't we talk about like, I guess some implications of this or what it actually means. I didn't see the quotient topology on the list, so I didn't get a chance to review it. So
how about this? Yeah. Can I explain an example or try to explain an example? Yeah. So the example you gave over here was you take the real numbers and you associate or you create an equivalence relation x tilde y, where x is equal to y plus 2 pi. Here implicitly you can put an n. The idea is that you're wrapping the line around. You're making this equal to this equal to this. And it's kind of like you're going around a circle. So obviously we've generated this set here, the quotient set using the real number. We still need to define the quotient topology, which is defined as this. And it's simple enough, right? So you just take all of the, let's just draw a circle for simplicity here. You take all of the possible sets that are a part of this here. And if they suck, if they're not good, like for example, if they have this point filled out and this point filled out, assuming we're using the standard topology on the real line here, then we'll notice that the preimage of this thing here is actually not an open set. Whereas if both of these are open ends, the preimage will be. So it ends up defining, or it ends up doing the exact same thing as the subset topology, but just, I don't know. I guess sometimes it's easier to think in terms of quotient sets.
Can we try bringing up like you know, some like not exactly a counterexample, but I guess maybe a counterexample, like some, you know, topological space, and then we define some like quote, like I guess equivalence relation on it, and then that seems reasonable. Like like we would intuitively think kind of glues two different parts of the set together, but actually ends up not, you know, we end up not being able to define a quotient topology on it.
You have something in mind that you want to demo?
In the definition itself, for the definition of the quotient topology depends on the existence of another topology already.
Of the original.
Yes, yeah, the original topology. David, let me get back to you on that. I have like one example in mind, but actually, whatever. I'll just say it. Let's say you have like just the sphere. So you know, the set of all points x, y, z, where
equals or smaller than.
Smaller than. So it's like cool. Hollow. Yeah. Actually, let's just do a sphere. Just equals.
Sure.
And then you glue two ends of the sphere together. So you say like you define an equivalence relation where 1, 0, 0 is equal to negative 1, 0, 0. You just glue two opposite ends of the sphere together. Okay. Okay.
It's kind of like you folded it on the inside.
Yeah. So like you kind of like take the two ends and you pinch them together, if you know what I mean.
Yes. Yeah. Okay.
Is that now? Can you like define the quotient topology on that, given, you know, that equivalence relation?
I think first thing is that I doubt that the equivalence relation is consistent.
What does that mean?
Like, what do you mean? If you have time, you want to go?
I mean, the equivalence, any equivalence relation is bijective to a partitioning of the set, right? So now you're just taking all your points, and like if each like point is its own partition of the set of all points, you just took two of those sets and merged them together into one set. In this case, your two endpoints that you pinched together, right? And I don't see any issues with that, because if you identify them to be the same object, then you just modify your topology accordingly, right? Like instead of having, let's say, it just works, because you say the two things are the same thing, and if two things are equal in a set, then only one of them is actually in the set. So it's fine.
Let me see that. I think there's like a way to present this that kind of gets rid. I'm looking through the notes I wrote a few months ago. I think there's a way to present the quotient topology where
It breaks
it's-
things.
no, where like on the contrary, it makes things a lot like more consistent and like easier to think about.
I think my issue is this: if you take a circle and we make this point and we bring it to here, we've like taken a circle and we've basically like folded it onto itself, and now it's a crescent, or I mean maybe a half cylinder, or no, semisphere. I don't even know. What happens at this point here?
Let me check.
It like folds onto itself. Like I'm not sure. Because this can this be continuous? Oh, I think maybe it can.
So I don't know how
Or-
useful this is to any of us, but
Okay.
I'm seeing let me clear my throat. Let's see. Where is it? Topologically, the pinched torus is homotopy equivalent to the wedge of the sphere in a circle. It is homeomorphic to a sphere with two distinct points being identified. Does that mean anything to anyone?
Sorry, say it again.
Yeah, that's I search up a pinched torus on Wikipedia. It has
Oh, that's an
diagram.
actual thing.
Oh yeah. So essentially, if I'm understanding correctly, which I don't think I am, it's
Oh
a
yeah,
sphere,
that
but
makes
with two
sense.
yeah, it's fine.
No, it's the pinch torus is what
Yeah.
you get if you take a sphere and you attach a circle to the surface of it, and then you kind of like wrap the sphere around the circle, if that makes sense.
It's the same thing you're saying. Just get two of the points to touch.
Yeah.
So it is a topology, so we're good.
Nice. The question is, do you establish that topology using? You probably could. If one way works and the other way probably also works too.
The only thing we're told is that the cohomology groups of P over the integers can be calculated. They are given by H subscript 0 P. Yeah, no. Any
Oh
of
my
you into
god!
topology?
Wow.
Like
Not-
mathematically?
Would you say?
I think Adar's a lot more into topology than me.
Yeah, Adar.
I was over the summer, but I didn't get very far in algebraic topology.
Oh, cohomology. You guys know what cohomology is? Like,
Nope.
No.
I couldn't explain it to you.
Oh, wow.
Some of the rough work I've been doing over the past 2-3 weeks has to do in homotopy, but that's not homology. It's just the only thing it shares is homo. And then
Yeah.
even then, I
Yeah.
can't describe to you what homotopy is. So yeah. it is
In
what
any
it is.
case,
Homotopy is just like a family of continuous functions between like two functions.
Yeah, something like that. And then yeah, paths, then paths between paths, and then you do that infinite times, and then you get what you call a weak infinity group point, and then you do stuff with that, apparently.
interesting.
Yeah.
On to the next topic we go. Adar, you want to explain product topology since you're familiar with it and some of the
Sure.
consequences? Here, let's divvy up the next topics. So you seem to be very familiar with product topology, and you can even introduce your
Box topology.
yeah. And then Taman, you can explain sequences and convergence.
Yep.
And then I'll try to explain, I guess, continuity and homeomorphisms.
Okay.
Sounds good? All right, let's go.
Yeah. Can I get a whiteboard?
Oh,
Here.
Does this work?
I mean,
I can go move to
a
the
whiteboard would be nicer, but what
Wait,
can use
actually,
Okay,
can
this?
you
cool.
just draw on the document itself? Is that a thing?
yeah,
Yeah, I
yeah,
can-
yeah, you can, yeah.
Oh yeah.
Like I'm thinking since the definition is behind us right here, it's nice because we can always refer to it.
Okay, sure. So,
Can you split screen and make like half of it white then? Can you like split the screen either horizontally or vertically so that half of it is writable and the definitions of the other half?
Oh, can I do that? If I could make the background white here, that'd be nice.
Like right
I mean, I
now
guess
you're right now you're sharing the window, right? Like just
Yeah.
your Chrome tab, like unshare,
Oh, I
then
see, I see,
reshare
I
your
see.
whole screen.
Okay, let me try that. We share full screen.
Okay. So
Hide thumbnail. Okay,
yes,
this works, right? Like
yeah,
you can
yeah,
write.
it
Okay.
works. Yeah, so the idea with the product topology is we want to have a way where if we're given two or more topological spaces, we want to define a topology on their Cartesian product in a way that's, that has like properties that we like, I guess. So one way that we might define this, and the definition I'm going to give is going to be different probably from what's on here, but it's going to be equivalent. I believe my definition, like the one I'm about to give, is going to be like easier to understand. So given, let's call our spaces xi, which is like, I guess, like a collection of spaces.
Which kind of spaces? Topological spaces?
Yeah, topological spaces. The topology, or like the product topology on this, on the product of all of the topological spaces, is a set, which we'll call, I guess, P, because why not, where a subset U of the product is said to be open if for each U, for each of these,
Yeah.
or I guess, for each of these, UI is open in okay, this is, I'm kind of like butchering all of the formal notation, but basically we have our product P, and we say that U, which is a subset of this, product, is open in P if if U is open in each of like the individual topologies, right? But
That's
there's
sensible.
a catch. There's a catch.
Cool.
And the catch is that that UI is a subset of Xi for only finitely many UI. Okay, so let me give you like an example of what this means. If you have a product, which, and this is just R to the omega, where omega is just defined to be like countable infinity. So you can even think of it as R to the n. That's just like another way to think about it. So just the point is, like, this set is just x1, x2, dot, right? In this set, the subset of this set, which we'll call the subset, like if we take a subset like -1, 1, -1, 1, -1, 1, and so on, this would not be considered open under the product topology. Okay,
Why?
because that's how it's defined. So keep in mind,
But they're all open. It's open here.
Exactly.
Open here.
Yeah, they're all open. But the additional condition in the product topology is that only finitely many UI can be subsets of their respective like space. Right. And the rest must be the entire space. So one topology that would be considered, or sorry, one subset that would be considered open is -1, 1 for finitely many of the
yeah, I see.
Of the spaces, and then for the rest of the infinity, it's just all of R.
Okay.
Right. So I get the condition, but I don't see what breaks if I remove
Yes.
the condition.
Yeah, so now
Same
let me
question.
let me give you an example, okay? This is where an example is good. Let's take the function f from r to r omega. I used to have like a better explanation for this, for why this is true, but I just forgot it. So I had to kind of like look it up again today. But we'll define this function as follows.
Okay, so is omega here a variable or omega here the first infinite cardinal?
Yeah, infinite cardinal. That's countably infinite, which we'll just define to be this.
So a function from a real number to an infinite sequence of real numbers.
Yeah.
Okay.
Right. So now, if this function is to be continuous, then for any open set in the like image, the inverse of it must also be open, right?
Yes.
Okay. So let's just suppose for a minute that instead of that added condition where only finitely many of the U. So remember, we had our like, product of open sets, right? Of all of the individual spaces, like U1, U2, and so on. And we said that in the product topology, only finitely many of these can be subsets of their spaces. And for the rest of them, U has to equal the entire space. So in this case, for the rest of them, U has to equal R, right?
Right.
Okay, let's remove that condition for a sec. So now a subset in the product, or in this is actually called the box topology now. So a subset of the box topology is open if all of the individual subsets are open. Okay, it's simple as that. So now we take the product, we test for continuity. So we choose an open set in this like, I guess, ordered pair. We choose an open set. Yeah.
Real quick question. Basically, you're saying I want this to make sense, or I want continuity to make sense in this case, and I shall prove that if this condition is not imposed.
Yeah, we don't have like continuity isn't as nice as we want it to be, basically.
Okay, I see. Okay.
Okay. So now we choose some open set in R omega, and we'll define this open set to be this. P of -1 over n to 1 over n from n equals 1 to infinity. Okay. This is our open set.
Mm-hmm.
Now, if we want to take the inverse, and we'll call this U, okay, just so I don't have to write it again. Now, if we take the inverse of this open set, inverse of U, what do we get? What is going to be the set that we get?
It's going to be, let me think. F of x is equal to f of x.
I guess just 0.
Yeah, exactly. It's just going to be equal to 0. And as we know, 0, the set 0 is just closed in the standard topology in R, right? So David, do you understand how the inverse of this
I don't see why it's 0.
Okay. So let's just say that
Wait, can you maybe explain to me what U is again?
We'll use a product of intervals, right? An interval, each interval is open in.
I think maybe what I don't understand is this symbol here.
This is like an iterated Cartesian. So just like you have like an iterated sum, right?
Oh,
this is just an iterated Cartesian product. So this is the same as saying like -1 over 1 1 over
Okay,
1
okay.
times and so on and so forth, right?
Sure.
So what this is going to look like, actually, maybe I shouldn't have erased it, but it's going to be, it's going to look like the first one is just going to be -1 to 1, right? And the second one is going to be -1/2
Okay.
to 1/2. So if we just take these two alone and we take the inverse of this, then the inverse is just going to be, it's just going to be, what is it going to be? I believe it's just going to be like from -1/2 to 1. I believe the inverse is just going to be -1/2 to 1/2. Ignore the F.
Yeah. Wait, no, in any case, the point is that, okay, you get 0. This is obviously like kind of is shit for continuity. How does having an R here fix the problem?
So having an R prevents this because, or having like infinitely many R's prevents this because it just doesn't go to 0. So no matter like, as long as n doesn't go to infinity, n could be like a trillion, right? N could be a trillion. And then the like your inverse of the set will still be really small, but it won't be only 0. It'll still be open because the rest of them are all of R.
Okay, I see. Okay, that's cool.
Yeah, like this explanation could definitely use, some polishing up,
And
but
waviness.
yeah,
Or, I mean,
hopefully it makes sense. There's actually like the original definition of the product topology that I read was in terms of subbasis. So you define a subbasis for the product topology, and then you generate the product topology from that. But I
don't know what a subbasis is.
a subbasis generates a basis, which generates the topology. It's not that like complicated, but yeah, I guess it's just
I'm sure.
added
No, yeah, I'm
machinery.
sure. Yeah. Like I could understand it rather quickly.
But yeah,
in this case,
hopefully you see how that wouldn't happen if you impose that additional condition where U equals the entire space, in this case R, for all but finitely many of the for all but finitely many U.
Yeah.
But yeah,
that makes sense to me.
That's that.
Cool. Taman, you want to explain convergence?
Yeah, so a sequence converges if at every step there is always an open set that contains all of the things in there that is smaller than all the open sets that came before it. Essentially, open sets shrink as you roll along.
Okay, yeah, I guess that's what I was thinking. Yeah, maybe we thought of it a bit differently. You think of it in terms of open sets getting smaller. I think of it as in all open sets contains all future points in the series, or there exists an open set that contains all future points in the series.
Yeah, exactly. That's kind of like the way to state it. That's more in line with the actual definition.
Okay, good.
You have like a sequence of points, and it converges if for each of those points, and like they're ordered, right? So you have like x1, x2, and so on. And for each like neighborhood U of X, there's a there is a positive integer n, where for all n greater than that point, they're all inside that neighborhood. Exactly. That was probably a pretty bad explanation, but
yep,
made sense. Let's see, and then I go on to continuity. Okay, this one obviously pre-image of open sets are open. Okay, specifically, I just absolutely love this example here, but it's like if you take an open set on the y-axis, there's like a really sneaky thing that happens whenever a function with a standard topology isn't continuous, which is that the projection ends up giving you an actual dot, which obviously is not an open set.
Wait, I don't follow.
Yeah. So definition of continuity. First of all, we agree that this function is not continuous. So what I will do is I will go and rigorously prove it. First of all, I start by selecting an open set on the target. And then I'm going to follow the pre-image of that open set I'm just gonna draw the line, then go down. And in this case, the point here would go to the empty set. The point here would go to the empty set, so it's just not drawn. But the point here actually goes to the dot, goes down, and the pre-image of this open set is not open.
Oh yeah.
So that's continuity explained. See, is there anything else to explain? I believe homomorphisms, but I don't know, it doesn't seem to have a section. Yeah, I don't know, I guess homeomorphisms, not homomorphisms. Yeah, so when you're dealing with just sets, you can have a bijection between two sets. The idea of a homeomorphism just expands that, but with topological spaces, where obviously the sets, there needs to exist a bijection between the sets, but there also needs to exist a certain kind of map, or over here. Well, basically there exists a, okay, I guess it needs to be bijective between N and M, but also the map between N and M and N and M, okay, funny, has to be continuous on both sides, which ends up implicating something about the topologies having a nice relationship with each other.
Isomorphism, but for
Yeah.
topological spaces.
Yeah,
Everything's an
yes.
isomorphism. All the functions we care about are at least homomorphic.
Yeah. What I'm wondering is maybe
Well, no, it actually says it's here, topologically isomorphic. So yeah, you're entirely correct.
I think maybe bijection is not actually might not actually be a necessary part of the definition. Might be wrong about that. But I think
So without bijection, you're just left with a homomorphism. You need bijection to become an isomorphism, because isomorphism.
No, so what I'm saying is maybe just the condition that both the function itself and the inverse are continuous, maybe that alone is enough to imply that it's a bijection. But I don't know. That's just like a hunch.
I don't
What
think
if you what if you equip both with the discrete topology, or like a topology that is just weird?
Well, you know it's invertible, but you need to know that the domain is it covers its domain, right?
Yeah,
and
I
therefore
guess.
you need bijection. Like,
Yeah.
sense? Yeah.
Yeah, no, I think it's wrong. Yeah.
And I guess one last thing to mention is that a really common thing from now on is that we're now able, like we've created homeomorphisms. So we've created structure preserving maps on topological spaces. And a really common thing in mathematics is to start classifying these spaces based on structure preserving maps, which is obviously the whole idea with classification of sets, right? With like, okay, this X and Y have the same political opinion, and then boom, you classify Democrats and Republicans in the US. In this case, you say X and Y have a homeomorphism between them. Let's say you pick a specific one. You need to pick a specific one, I believe. And then you can classify with has it and has not. And you're starting to classify spaces.
Sets are a bit uninteresting as far as isomorphisms and classifications.
Yeah, because it's just like cardinality.
Yep.
What about topological spaces?
I've never worked with topological spaces. I don't know which invariants they preserve there.
They're definitely more interesting than sets.
Yeah, okay, that's for sure. But I think that's
I can talk a little bit about what they preserve.
That's next. Are you going to be talking about like compactness and stuff or something?
Yeah.
Yeah, so that's next lecture.
Okay.
So I guess this is just a hint for next lecture, like with homeomorphisms, that like the point of caring about this is to start talking about those invariants.
By the way, Adar, are topological spaces generalizations of metric spaces in any way?
Like yes, and I guess the answer would be yes.
So is there a metric space that is not a topological space then, or is that just?
Yeah, I don't think there is.
Okay, gotcha. Just wondering about it.
Because I think the point is you can create a metric space from a topological space. I'm fairly certain.
Well, there's this
I think
notion
it's the other way around. From a metric space, it already has an existing topology. You just like added the extra concept of distance.
Yeah, exactly. Yeah. They're like a space is like metrizable I believe is the word. Like if you can make a space a metric space, then first you need to define like a distance function. That's kind
Okay.
of the, yeah.
Kind of like if you have a group, then you have a vector space in some sense. Yeah.
Or yeah, like a group in a ring. But actually, I think it's even like I think like the like relationship and how they were developed was different than that.
Yeah.
Like at first we had metric spaces, and then like, you know, mathematicians
yeah,
started
definitely.
noticing that they could, you know, define even less structure while still talking about the same properties.
Yeah.
How did Euclid go for you, by the way?
Oh yeah, I'm kind of pissed because
Same.
No way.
I just assumed that like question 9 and 10 would be too hard. So I didn't even realize how easy 9A was.
Yeah.
So I just didn't do 9A, even though like I looked at it the next day and I was like, bro, I could have done this in 2 minutes.
Yeah. I was pissed because like the previous years I practiced previous years and I was hitting like consistent 95s to 98s.
Oh my
Damn.
And then I
God.
do like the actual test and I'm pretty sure I only barely got over 85. So that was
Yeah.
Damn.
because I'm trying to get into the advanced math selection courses that they offer
Oh,
at
cool.
Waterloo.
Yeah.
But the cutoff for that is like a Euclid of 90.
Yes,
so like this was the
exactly.
test result that I actually needed, and then I don't have it now. Which is
Damn.
annoying. Yeah.
Yeah, I did all of them up to like 8B. And then with like the like 9 and 10, I didn't really look at 10. And with 9A, I'm just mad that I could
3 points. How many
yeah,
points was it?
probably around 3.
Okay,
Yeah.
so it's just acceptable.
I feel happy that first of all, like score wise, we're way above the average. But at the same time, I'm just kind of pissed just because I know I could have pushed just a little harder and got it. But
Yeah.
it's fine.
Oh well.
All right. In any case, nice conversation, guys. Yeah, we'll talk potentially next week.